Greetings, class. I want you to imagine a scenario with me for a second. Picture yourself in a gym, and you are holding a massive 100-kilogram weight directly above your head. You're holding it perfectly still. Your muscles are burning, your heart is racing, and you're putting literally every ounce of your energy into just keeping that heavy barbell exactly where it is.
Now, you might feel absolutely exhausted, right? But the irony is, according to the strict laws of physics, you've done absolutely zero scientific work. None at all. I know, it sounds totally counterintuitive, doesn't it? But understanding why requires us to completely rethink the vocabulary we use every single day. So today, we will study principles and calculations of scientific work. Let's establish our baseline.
Here is our absolute foundational definition for this explainer. Work is done when a force moves its point of application in the direction of that force. Really want you to memorize this. Sweat does not equal work. Pure effort does not equal work. Only a force paired with actual motion in a specific direction counts. So let's talk about why this is so confusing at first glance, and compare our everyday vagueness with scientific precision.
Here are the core details regarding this topic. Review them intently for their deemed crucial for your finals.
The reason that 100-kilogram weight example feels wrong is simply because of our linguistic habits. We toss around words like work, energy, and power all the time, but we use them very loosely. You might say, I just finished a ton of homework. But unless you forcefully shoved your heavy textbooks clear across the room, which, let's be honest, we've all wanted to do, physics says you haven't actually done any work. In casual conversations, work just describes effort or a task, but physics demands extreme mathematical precision. This everyday vagueness is exactly what trips so many students up. To really succeed here, you have to completely abandon your informal understanding of the word and rely strictly on the exact scientific definitions.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
Moving on, let's look at the specific variables involved. What actually triggers scientific work? If sheer effort isn't enough, what mathematical conditions have to be met? First, let's clearly define the point of application. This is simply the exact spot on an object where your force is acting. For work to occur, two strict conditions must be met at the exact same time. Condition 1, a force must be actively acting on the object. Condition 2, the object must actually move in the direction of that applied force. So, this gives us our crucial formula. Work done equals force multiplied by displacement in the direction of the force. Think about pushing a broken-down car along a flat road. If you push forward and the car rolls forward, your movement perfectly matches the force direction. You are doing work. But if you try to lift that exact same car completely off its wheels, the direction changes to vertical. That requires vastly more work, which is why we have to use machines like car jacks to pull it off. Direction is absolutely critical here. Now let's explore how the direction of force compares to movement and how that creates positive or negative work. In physics, work isn't just an absolute value. It can actually be positive or negative, and it depends entirely on those directional relationships we just talked about. When your force moves its point of application in the exact same direction as the force itself, you're doing positive work. You're doing work on the object, like pushing a heavy box forward across a room. But what if the direction of the force is exactly opposite to the movement? Well, then work is being done against the force, and we call this negative work. A perfect example is a braking car. The vehicle is displacing forward, but the brakes are applying a massive force backward. Because the force directly opposes the displacement, the work done by the braking force is mathematically negative.
Listed are the main insights for the heading discussed. Note them specifically since they are highly relevant for exams.
Let's dig a bit deeper into the math, specifically looking at how vectors interact to produce scalars. Notice that in all our definitions so far, we use the word displacement deliberately rather than just saying distance. Why is that? Well, because displacement is a vector quantity. It has a specific size or magnitude and a specific direction. Force is also a vector quantity. But here is a really fascinating twist of physics for you. When you multiply these two vectors together in this specific way, the work done becomes a scalar quantity. It has magnitude, so just a number, but absolutely no direction. We measure this scalar quantity in joules, represented by a capital J. By definition, 1 joule is the work done when a 1 Newton force moves 1 meter in the direction of that force. This means a joule is perfectly equivalent to 1 Newton meter. Of course, things are rarely so simple. Let's look at how we calculate work when things are at an angle.
In the real world, forces are almost never perfectly aligned with movement, and this is exactly where we have to introduce a little trigonometry. Force often acts at an angle, which we'll call theta, to the direction the object is actually displacing. Because of this, we can't just multiply the full force by the displacement anymore. Instead, we have to resolve the force into two separate components. The first component acts parallel to the displacement. Its value is F multiplied by cosine theta. This is our hard-working component. It does all the actual work because it perfectly matches the direction of movement. The second component acts perpendicular to the displacement, and we calculate that as F multiplied by sine theta. Now, because the object doesn't move at all in that perpendicular direction, this component is utterly lazy. It does absolutely zero work. So this gives us our general universal formula. Work done equals F multiplied by X multiplied by cosine theta. Our earlier simpler formula is really just a special case where the angle theta is 0, because as we know, the cosine of 0 is exactly 1.
Let's make this concrete. We'll walk through a classic worked example together. Imagine a child is pulling a toy cart along the floor. The string makes an angle of 25 degrees above the horizontal. The pulling tension is 1.5 newtons, and the cart moves 265 centimeters. Step 1, we need to identify our working component. Since the cart moves horizontally, only the horizontal component of that tension is actually doing the work. Step 2, we calculate it as 1.5 multiplied by the cosine of 25 degrees. Now for step 3, and I'm going to pause right here, because this is a classic trap in A-level exams. We absolutely must convert our units. Displacement has to be in standard SI units, which are meters. So, 265 centimeters divided by 100 gives us 2.65 meters. Step 4, we calculate the whole thing. Work done equals the horizontal force times the displacement. That's 1.5 times cosine 25 degrees times 2.65, giving us a final answer of approximately 3.6 joules of work.
All right, let's wrap this up with the high-yield review of everything we've covered. We've laid down a lot of precise scientific groundwork today. Please make sure every single one of these takeaways is committed to memory. Work requires a force moving its point of application in the direction of that force. It essentially mandates both force and aligned displacement. Remember, work is a scalar quantity. It's measured only in joules, where 1 joule perfectly equals 1 newton times 1 meter. If the force and movement are perfectly aligned, work simply equals force times displacement. But if there's an angle, work equals F times X times cosine theta. Never forget that the perpendicular sine component is lazy and does absolutely zero work. And lastly, work is positive when directions match and negative when they oppose. Before we go, I want to leave you with a really fascinating puzzle based on exactly what we've learned today. I want you to think very carefully about the angles involved here. If work requires force to be perfectly aligned with displacement, how much work does Earth's gravity do on the moon as it is continuously pulled perpendicular to its perfectly circular orbit? Think about the angle between gravity's pull and the moon's actual path. Apply our formulas, and you might just find an answer that genuinely surprises you. Class dismissed.
Important terminology for this topic is shown on the screen, arranged according to various exam boards. These terms demand focused attention during revision as they are highly significant and must never be overlooked. Furthermore, a past paper evaluation is included for each board and paper format. Give this paper attention too, since it will strongly enhance and refine your preparation. Additionally, aims to grasp the meaning and usage of every term instead of rote learning them individually. Consistent practice of these terms in past paper questions will greatly boost your precision and overall exam results.
Please subscribe our channel to get more educational videos. Thank you.